Hello, in this video, we're going to look at the binomial series a little bit. So we're going to use Taylor's theorem directly to find a Maclaurin series for the binomial 1 plus x raised to a constant real number power p, 1 plus x to the p power. So and n is going to take account of which term we're in. So the zeroth derivative, or the function itself, is 1 plus x to the p. The first derivative then is p times 1 plus x to the p minus 1. Then another derivative, that's p times p minus 1 times 1 plus x to the p minus 2, and so forth. There's a nice little pattern there. Evaluating at 0, all of this 1 plus x to whatever power just becomes 1. And so we get 1 p times p minus 1, p times p minus 1 times p minus 2, p times p minus 1 times p minus 2 times p minus 3, and so forth. So each one of these, the nth derivative evaluated at 0, is p times p minus 1 times p minus 2, all the way down to p minus 1 less than the n. So that's the product from k equals 1 to n minus 1 of p minus k. So it's the product of n factors starting with p, and each successive factor decreases by 1. Now we've got to divide this by n factorial, which of course is the product of just k from 1 to n. Okay, so this is, we end up with the product from k equals 0 to m minus 1 of m minus k. So m minus 0 is there. Okay, so this would be the m term, m minus k, and then p minus k here. So in top and bottom, they're both n factors. These are the first factors from 1 up to m. These are the factors from p down. Okay, and this is another way to write it here. And this is written, these are called binomial coefficients because they come from this binomial expansion. They're written a couple of different ways. One is this, pm, like this, one over the other, no fraction line or anything, but in parentheses. Another way is pcm. This is often pronounced p choose m, and sometimes they're called combinations as well as being called binomial coefficients. Okay, so here m is going to be a whole number, but p is allowed to be any real number, not just a whole number. Now, in some contexts, we apply this where p has to be a whole number bigger than m, but in this context here, we're letting that relax a little and let p be any real number. P choose 0 is 1, and then this works for where the second number there, the bottom number here, is anything bigger than 1 would be worked out with this product here. So that is the coefficient for this series. So 1 plus x to the p is the sum from k equals 0 to infinity of p choose k, x to the k. So that's 1 plus p times x plus p choose 2 x squared. P choose 2, remember, would be p times p minus 1, so 2 factors there, over 1 times 2, 2 factors there. Okay, and reduce that if we need to, depending on what p is. Then this is p choose 3 times x cubed. Well, what's p choose 3? Again, that's p times p minus 1 times p minus 2 over 1 times 2 times 3, and so forth. And it turns out that this is going to converge between -1 and 1. Okay, I guess we would need to use the ratio test to confirm that part there. I'll leave that for an exercise. If p is a natural number, then at some point, this product here, one of these things, like if p is 5, the next one, the sixth one, is going to have a p minus 5, which is 5 minus 5 is 0. And then from there on, the derivatives are all going to have that factor of p minus 5 in them, and they're all going to be 0. So if this is a natural number for p, then at some point this drops out. In fact, it drops out right after it gets to p, right? So if this is p is 6, then the 7th term on will all be 0. Okay, and we get a 6th-degree polynomial, which is, of course, what you'd expect. But if p is something that's not a natural number, like p is a 1/2 power or something like that, then you're never going to get one of these to be 0, and this thing is going to go on forever, giving us an infinite series, a binomial series. When you have p as a natural number, there's an interesting relationship with these things coming from something known as Pascal's triangle. And they also give a nice counting technique use for these binomial coefficients, also known as combinations, as the way, so if you have p, choose k, it's a way of choosing k objects from p distinct objects where the selection is done without repetition and the order doesn't matter. So we study these quite a bit in probability theory, where we're interested in counting up some things like this, or in the theory part of math called combinatorics or discrete math. So those are some different subjects where this is going to come up. And so I have 3 videos here from my statistics classes showing where we would use these binomial coefficients. But in that case, we're always looking at where p is a whole number, in fact, a whole number bigger than k. Okay, so use power series to find a Maclaurin series for arc sine of x. This is another problem that we can do, and it uses the binomial expansion. Let's go ahead and do that. So this is a little more challenging one. The derivative of arc sine of x is 1 over the square root of 1 minus x squared. So we're going to need a series for 1 over the square root of 1 minus x squared, and then we can integrate. Okay, so we're going to do a binomial series with x equals, the p equals negative 1/2. So 1 over the square root of 1 minus x squared is almost this. So 1 plus x to the negative 1/2 is kind of what we have here with p is what's exactly what we have here with p equals negative 1/2. So this is negative 1/2, choose k, x to the k. So it's we can kind of work those out. So this is, of course, the first one here is just 1, and then you get negative 1/2 for the coefficient. Let's see, because it's well, it's over 1 factorial, which is 1. You get negative 1/2 minus 0. Okay, and the next one's negative 1/2, but then it's times negative 1/2 minus 1, which is negative 3/2. So you got 2 factors there. Here you got 1 times 2 in the bottom. Okay, so that reduces to, well, basically 1 times 3, and we get 2 to the, well, a 2 square, and then we get this 2 factorial. All right, then the next term, you get a negative 1/2 times negative 1/2 minus 1 times that minus one other 1. That's negative 5/2. So you get those 3 terms. So that's going to give us a 2 to the 8th and a 2 to the 3rd in the bottom, which is 8. And then we're going to get this 3 factorial in the bottom. And we get a 1 times 3 times 5 in the top, or just 3 times 5. And let's see, we have 3 negatives, so that one's negative. 2 negatives here made just a positive. Okay, so we got 1, 2, 3, 4 negatives makes positive on the x to the 4th term. We got our 4 factorial in the denominator. We get the first 3 factors like we had here, and then we go down 1 more. It's negative 7/2. So we got 1 times 3 times 5 times 7 in the top, and 2 to the 4th times 4 factorial in the bottom. And that pattern keeps going. So you got the next one should have 5 factors. I got to fix. Okay, so they have 5 factors, the same 4s we have here, and then the negative 7/2 minus 1 is negative 9/2. So in our top we have 3 times 5 times 7 times 9 times 1 if you want. We have 2 to the 5th in the bottom with a 5 factorial there. We have 1, 2, 3, 4, 5 negatives makes a negative there, and this pattern kind of continues on. So we end up with an alternating series. So it's negative 1 to the k. I'll put the first term kind of separately. Then this is the product from j equals 1 to k of 2j minus 1. It's above the odd numbers, right? And then the bottom is 2 to the k and a k factorial, and then we have x to the k. and it's going up one at a time. Okay. Now, if we take this 1 over the square root of 1 minus x squared, it's the same thing, but we replace x by negative x squared. So if we put a negative x squared in here, so we got negative x squared and then raise it to the k, well, we got that gives us an x to the 2k, but we have a negative 1 to the k, and that negative 1 to the k are going to cancel out. So now we're all back to positive terms. Okay, so now it looks like the same thing we had up here, but only with positive terms, and now the powers are going up by 2. So even power terms. All right, so that's the series for that. Now that is the derivative of arc sine, so the arc sine is going to be an antiderivative of that. So the antiderivative of this 1 over square root of 1 minus x squared is the antiderivative of this series. Antiderivative of 1 is x. I guess I need to put a plus c0. And then this is the sum of these antiderivatives here. So all the powers go up by 1, and we divide by 2k plus 1 factorial, same as the power. The rest stays the same. Now the arc sine of 0 is 0, so all these terms go to 0, leaving the c0 to be whatever arc sine of 0 is, which is 0. So that term's gone. No constant term, so we get this. So we end up with only odd powered terms. Here it is kind of worked out. It's x, then 1 over 2 times 3 x cubed. Then this, so that's just a 1. Then this is a 3 here for the next one, and a 2 squared, 2 times 2 factorial times 5. Then this is going to be a 3 and a 5 in the top, a 3 factorial in the bottom. It's okay, a 2 cubed, and the 7. Next one's going to go up to have a 4 factorial. The power here is going to go up to 2 to the 4th. And then instead of a 7, you got the 9 from here. And the top is going to be a 3, 5, and a 7 multiplied together, and so forth. So this continues on. Some of this will reduce, which I've done some reducing here, and then multiplied out to get this here. So we're using k to represent the number of non-zero terms in the series. So this is 1, 2, 3, 4, 5, and so forth for k. Actually, k starts with the second one. So k is 0, then 1, 2, 3. Okay. And we work on there, work through that. Represent say starting with 0. So that's correct if I say I'm starting with 0. And before reducing, we have that pattern that we see that I've written out here. So that's a little bit of a more complicated one. So let me real quickly summarize some of the standard power series that we've worked out in this video and some of the previous videos. So first of all, a geometric series, 1 over x. One way we can do that is center it at 1, and we get the sum from n equals 0 to 1 to infinity of negative 1 to the n, x minus 1 to the n, like that. These come from a geometric series. That's valid from 0 to 2, non-inclusive. 1 over 1 plus x is the sum from n equals 0 to infinity, negative 1 to the n, x to the n. It's worked out like that. Those are alternating series. Natural log of x we can find centered at 1 as this way, negative 1 to the n plus 1 times 1 over n times x minus 1 to the n. You see it worked out there. That's the value from 0 to 2, 2 included but not 0. E to the x is a particularly nice one. It's just x to the n over n factorial, all positive terms, valid everywhere. Sine x is the odd terms from e to the x, but then with an alternating sign. Cosine x is the even terms from e to the x with an alternating sign. Sinh of x is the odd terms from e to the x, not an alternating sign. Cos of x is just the even terms from e to the x. Arctangent of x is odd powered terms, alternating sign with the coefficient being reciprocal of the power. And the binomial expansion that we just did is 1 plus x to the nth power is the sum from k equals 0 to the n of n choose k, x to the k, like this, and we defined above what that meant, and that's valid from -1 to 1. So if we took some of these as being known standard power series, we could work with these perhaps to get some other power series by, as we've seen in the last couple of videos, multiplying series, dividing series, substituting in, integrating, or differentiating, or some combination thereof to get some new series from old series.